real exam questions. This is question 4. It's about ultimate limit state. The question goes as follows. What assumptions are made when calculating reinforced concrete in the ultimate limit state persistence? First, we assume that plane cross-section remains plane before and after loading. So this assumption means that strain at any point of the cross-section is directly proportional to its distance from the neutral axis. So, and means that the strain diagram is linear. Let's look now at a beam on two simply supports. That is the height of the beam. We look at those two sections. And this section, all points on this section before loading will be on this section after loading. So that was what this means. Or you can look at in a further detail. The gray one is before loading, purple one after loading. And if you look at the section in more detail, you will see that the dotted line is before loading. That's a strain diagram here. And after loading stays a plane. So this is in one plane. All those fibers in one plane, they stay also in one plane after loading. So top side is compression or shortening. This one is shortening. And the bottom side is tension, is elongate. Second assumption is that there is a perfect adhesion between reinforcement and the concrete. This is control section in a concrete beam. This is the concrete, and there's the reinforcement. This is before loading. Everything stays here in one plane. After loading, so this section gets tilted. When you have after loading that the strain in the concrete is different than the strain in the steel, then you have a situation like this. So this is not the case. We don't want that. The assumption is that the strain in concrete and steel is the same, so it will look more like this. The stress in the rebar is of course equals to the strain times the modulus of elasticity, and the same for the concrete. We know now that locally the strain of steel and strain of concrete is equal to each other. So this leads that those two proportions are equal to each other. Or you can write it in a simple way. You can say that the stress in the steel is equal to alpha times the stress in the concrete, and alpha is the proportion of the modulus of elasticity of steel and concrete. And the perfect adhesion here leads in fact to an elastic behavior of the material. Be reminded that this equation is only valid locally, local, not outside, it's local. Assumption is tensile strength of concrete is ignored in ultimate limit state, but we should immediately correct this because for the anchorage of reinforcement, you need tensile strength. And for shear resistance, which is ultimate limit state, you need also the formulas of shear are based on tension strength of concrete. So, but in general, the ultimate limit state, tensile strength of concrete is ignored. We have the strain diagram with a load, and on top we have the compression strain, and at the bottom the tension strain in the reinforcement. We bring this to stresses. then we see the green is a compressive concrete stress. The blue one is the total force in the reinforcement. And you see that in ULS, we do not count on the force of tension in the concrete. So otherwise, something must appear here. So we say that below the neutral axis, the contribution of the concrete is 0. Another assumption is the stress in the concrete in compression follows the parabola rectangle diagram. So again, we have the strain diagram and we have the stress diagram, and it's about this green diagram. It says, if we enlarge it, that it is composed of a parabolic situation like this plus a rectangle one. And the parabolic portion goes until a strain of 2 per mil, and the maximum strain is 3.5 per mil. The maximum stress is FCB. This is valid, of course, for concrete quality smaller or equal to 50 megapascal. And the equation or the relation between the stress and the strain, and let's give you this curve, is equal to this formula, depending on those two, depending on this value. The concrete strain of the ultimate concrete strain is 3.5 per mil. So this is also an assumption. The next assumption is the stress in the reinforcing steel is derived from a bilinear stress diagram with a horizontal branch. I know there are other assumptions too with an inclined branch, but we will concentrate us on the horizontal branch. So this is the stress and this is the strain, and it has a bilinear connection between the two. The strain at the point where the steel is yielding is then equal to 2.17 per mil. The maximum strain in the steel is 10 per mil. Bear in mind, this is an assumption of the Belgium annex to the code. So the reinforcement strain is 10 per mil. And the modulus of elasticity of the concrete is 200,000. It is the same in tension as in compression. These are the other two assumptions. And in the annex in the Belgian annex, epsilon UD is 0.8 times epsilon UK, but we limit it to 10 per mil. Just bear in mind, if you look at this diagram, when converting strain to stresses, that if the strain is smaller than this value, then the stress is epsilon ES. If the stress is between this value and this value, it's the yielding of the steel line, yielding of the steel. And when epsilon bigger than 10 per mil, we do not allow it. We will prohibit it. Another assumption is that the actual compression strain epsilon C2 is 2 per mil. That means when you only have compression, external forces, internal forces, that the maximum compressive strain is 2 per mil at pure normal forces. Again, you will see it on this diagram. It stops there. The loads act in the vertical plane of symmetry of the cross section. You have, for instance, here a beam. You have the control section, the vertical plane, and we have the point of gravity, the normal force acting in vertical plane of the cross section. For instance, for a bending moment, we assume that the bending moment is acting like this. And for a torsional bending moment, it is acting in this plane, like that. And of course, you can have a point load. The point load is assumed to act like that.